All right, we are getting started. This is a big week for us. A study guide was released on Friday. It has not covered the material that we've covered in about the last week. So there'll be a little bit of thinking backwards, but I also was very okay with that because that meant that there was nothing that was incredibly relevant on the current homework. There was a little bit of it, but it didn't feel to me like I needed to say, get it in by Monday if you want people. Because for the most part, a lot of the difficulty of this exam came from the last homework, not the one that's due on Wednesday. That said, if you'd like to get it in by today, I can see if we can turn it around by Friday. In case there's anything on there that you would like to have feedback on ahead of the exam. But again, remember that the cutoff on the exam study guide is the cutoff for what I will be asking people about. As usual on exam week, we're going to have a study session, a review period on Thursday for the entire class. So please come prepared with questions or something you'd like additional examples with. I think I'm already planning to do a bit with pumping lemma because that is certainly the big challenge of this exam. But any other questions or concerns before we dive in?
People get feedback on the homework.
Yes, yeah, I think we're very close to done with that. So you will certainly be getting that over the next day or two at the latest. Yeah, there's a lot happening this week, especially for those in game dev as well. We have an exam on Wednesday in that class as well. It was an unfortunate reality. I was gonna try to make it last week, but I didn't really want to get in the middle of our party last week. All right, so last time we were talking about Turing machines, and then we talked about what would a non-deterministic Turing machine look like and act like. That was a very intriguing concept. We said nothing really changes, but now if we add the concept of parallel choice, what does that do to the power of the language or power of the system? Does it make it more powerful? Can it solve different problems than it could deterministically? We defined this concept of, since we have a large amount of parallelism in this, any of those threads can either reject or enter an infinite loop, and those don't really matter. It's just a matter, does a single thread lead to acceptance? The issue with non-deterministic Turing machines is, how do we notice that a thread has entered an infinite loop and is not just taking a long time to produce an answer? So the reason we don't study non-deterministic Turing machines at a great level of depth at the moment is that we don't have an easy way to explore that problem. In fact, we can show that there is no generic algorithm for recognizing an infinite loop. And we'll get into that this week. But that's why these aren't particularly interesting. If we can eventually get some quantum computing online, then maybe this becomes a more interesting problem. But at least for now, we're not really too terribly concerned with non-deterministic Turing machines. But what happens with them? We said what we could do is we could feed the non-deterministic Turing machine into a deterministic Turing machine. So the deterministic Turing machine, you can imagine that it's one with just an infinite number of tapes or a large number of tapes, and that way, whenever the deterministic Turing machine would work, then the non-deterministic Turing machine just starts that computation on a next tape. So that's how we can show that it's not really a different class of algorithm. The interesting computational component of this is the NP completeness problem that you may have seen in other classes. So I guess maybe I can take a stab at that. Who's seen and heard of NP completeness in other classes? All right, it's definitely something I should go over then, because it's an interesting problem type. Maybe I'll hold off on that for a second, but I'll make sure that I cover it at some point. It's a very important problem in computer science. So if you continue this line of thought, apply some math, that's in the textbook that I'm not going to go over, you can eventually find that if you can make a non-deterministic Turing machine, there is an equivalent deterministic Turing machine for it. So it does not solve any more complicated problems. It's just significantly more efficient. And we find this in terms of NP completeness as well. Maybe this is the time to go talk about it. So there's an entire class of algorithms out there that in terms of a deterministic solution, we cannot do better than exponential complexity. However, if we allow non-determinism into that, we can get the complexity down into polynomial time. No math proof exists that given that we can solve the problem non-deterministically in polynomial time, we either can or cannot solve the deterministic version of that problem in polynomial time. We just know that we haven't been able to so far. And there is a very large prize out there for anyone who is able to prove this. Mathematicians and computer scientists have been trying for decades with absolutely no headway. There have been some proposed proofs, but they always have errors in them. What we can do in the meantime is add to this class of languages that says, all right, I have this problem. I know this problem is NP complete because I can show that there is an exponential time deterministic algorithm that solves it and a polynomial time non-deterministic algorithm that solves it. Great. Now, if there's a polynomial time algorithm that converts this problem into another problem, we can add that to that same class in a way that says, if we can solve a single one of these problems, then there exists a polynomial time conversion to solve all of these other problems. So all we have to do is solve one of these problems, and we've solved all of them deterministically in polynomial time. So an algorithm that is NP complete or a problem that is NP complete is in that class is one that we don't know. We don't know if it's solvable deterministically in polynomial time. One such one is the traveling salesman problem. If anyone has seen or heard of that in prior classes, the idea is to have a graph, and maybe this graph represents cities and distances between cities. We want to find the shortest path such that this salesman starts in a city, traverses the graph to every other node in the graph, and gets back to where they started. But we want this to be the shortest possible path for that cycle. And that is an NP-complete problem. As the graph scales in size, you have to look at every single possible path in order to be able to conclude that this is the best path. There's no easy way to shorthand and get some information about that in a way that makes it less than deterministic exponential time. If we can find a way to do that deterministically in polynomial time for an arbitrary graph, then we've made a lot of progress and probably broken the internet along the way. A lot of our security measures in place all rely on this fact that NP-complete algorithms cannot be solved deterministically in polynomial time. So that's the basic intro to that concept, because we're going to be using something that's very similar with a class of algorithms with Turing machines. But we're not so much concerned about their running time as we're concerned with their solvability. Can this algorithm can we answer this question both yes and no? Or can we only answer it yes or only answer it no? But to do this, we actually have to define a new concept of Turing machine. We're going to call this a universal Turing machine. Even though I've said that Turing machines and modern computers are basically equivalent, there is a big difference between them. And the big difference is that the modern computer is reprogrammable. We can make a change to an existing algorithm by loading up the source code and making a change to a single line, and everything else stays exactly the same. How would we do that in a Turing machine? You have to make a general change to when we're in this state, reading this symbol on a particular input, we make a change to that. And as the best that we've shown so far, we can't do that. We have a definition of a Turing machine and it's locked in place. The transitions are set in stone. We can't make changes once we make this machine. So what would we need to do to a Turing machine to make it reprogrammable? And the answer to this lies in the fact that instead of having an input representing some kind of string on the tape, instead, we are going to find a way to write on the tape a definition of another Turing machine. If we can find a way to make a string that represents a Turing machine, then we could make a Turing machine that runs the execution defined by the other Turing machine on its tape. Yeah. So a Turing machine is going to now take as input another Turing machine. So its string will be the states, the transitions, which of those states are final, when does it halt. All of that information will be embedded on the tape of the Turing machine. So this is what we're going to call a universal Turing machine. It's no longer looking at a single string for acceptance and rejection. It's now going to emulate what another Turing machine that's described on its tape says. This is another place that we could come back at the end of the quarter if there is time. I'm not sure if there will be time, but the end result from doing this is that we can encode a Turing machine as a binary string and then just throw that binary string on the tape, and we get the ability to emulate, or the ability to read in instructions and carry out those instructions, which is exactly what a modern computer does. Reads in instructions, carries out those instructions. What's nice is that we can show that for a particular binary string that will map to one and only one Turing machine, if it maps to a Turing machine. There'll be some binary strings that don't map to a Turing machine. But if you iterated all possible binary strings, what this does is eventually you would be able to represent every existing Turing machine on the tape. Again, imagine we have literally forever to do this. You would start on the tape, just 0, 1, 1, 0, 1, 1, just start iterating binary numbers. Some of them will represent instructions that lead to a Turing machine. Some of them will be garbage and do not represent a Turing machine. But as you did this process forever, you would be getting to longer and longer, more and more complicated Turing machines. And there wouldn't exist a Turing machine that you would not get to if you did this. Which is really interesting. That any program you could write, we could write an algorithm that just started generating programs forever. There is no program you could write that this algorithm would not eventually get to.
Does this follow like the monkey on the typewriter principle? We're given enough time, eventually it will make everything ever written.
Yeah, that's a pretty similar argument, except that the monkey doesn't have a prescribed process for this. Whereas for this, an algorithm would have a prescribed process. We can go prove that based on this algorithm, here is how many instructions we would have to feed before it generated print line, I hate my life 1,000 times. That is a program that eventually, that has a binary representation that would eventually be gotten to if we were generating all legal Java programs. You would generate all legal Java programs that have 1 instruction and 2 instructions and 3 instructions and 4 instructions. And there are a ton of those, but there are a finite number of them. As long as we say something like the names of variables don't matter. But even then, you could have all variables of length 1 and then the same programs for length 2. We'll actually talk about how this becomes a countable infinity, possibly today. Possibly tomorrow, we'll see. But coming back to this, we can emulate Turing machines. We can simulate the instructions that Turing machine tells us to do. And now we have a proper model of a computer, because a computer can be told, do these instructions and then do them. When we say something like calculate 7 times 4, we're not actually doing that process, but we can state that process and then the machine goes and does that. So a Turing machine would just be the sequence of instructions that lead to that. And that way you could feed into like a Turing machine and a string with a separator character, and then you could simulate what this Turing machine does on this string. So now you have a Turing machine that takes in other Turing machines. So you have a real computer. We're going to come back to this in a lot more detail, but countable and uncountable sets become a very important theoretical idea when talking about Turing machines and what Turing machines can calculate. So let's give an example to start. What is a set that is countable?
Natural numbers.
Natural numbers? Great. How do we know the natural numbers are countable? Yeah, you start, there's a starting point, and then there's a process to generate the next one. Given the current one, there exists a next one, and we can calculate, there's a formula to calculate the next one given the current one. It actually maps really well to the concept of induction. And if I'm teaching induction, then that's a lot of what I use dominoes, and I use the concept of positive numbers. How do we know that there's a number larger than a googolplex? We can add one to it and generate the next one. It's the process. It doesn't matter what the current number is. There is a process for generating the next one. So set of positive integers, is that countable? Yes. There's a defined starting point, and there's an algorithm to generate the next one given that we have the current one. So it is countably infinite. How about the positive even integers? There's a starting point, 2. We aren't going to count 0 as a positive even integer. So start at 2, and to generate the next one, given the current one, you add 2. How about the set of all integers? We actually discussed this a little bit on Friday. We remember what the trick is to making all integers countable? Now, this isn't just positive integers, this is all integers.
Yes, I think I actually did it in your office with you. There was an actual starting point where we more just create indexes for each possible integer that we can generate. And then there's some formula we can do to calculate that.
Yeah. So the starting point is 0. The successor to 0 is 1. The successor to 1 is -1. The successor to -1 is 2. The successor to 2 is -2. You just bounce back and forth between positive number and negative number, the next positive number and negative number, the next positive number and negative number. And you can now map all integers onto the positive integers, which is really intriguing to do. So let's actually come up with a function to do that. So on the top, I'm going to have positive integers, 1, 2, 3, 4, 5, 6. And on the bottom, I'm going to have this algorithm, 0, 1, -1, 2, -2, 3. Both of these go on forever. What is a formula that derives the bottom given the top?
Let's see. I could notice that the even numbers are all the positive numbers divided by 2, and that the odd numbers are the negative numbers.
Okay. So that helps us. If we just divide by 2 here, we get the appropriate number. How do we map the odds to these negative numbers?
You take the floor, divide by 2, and then take the floor of it, and then change the sign.
Yeah, so we could do something like -1 to the n followed by this value, whatever we want to call it. I don't know what we want to call it. Sure, we'll call it I. And you divide that by the position that it is. So I over n, take the floor. And that would allow you to generate the bottom given the top. There is no legal index for the top that we could not generate the bottom for. So given you gave me a number on the top, we could give you the number on the bottom. We could invert this. Given a number on the bottom, we could generate the number on the top. So this is what tells us, 1, that all of the integers are countable, and 2, it's actually the same size. And this is what is very difficult for a lot of people to grasp the first time you see it, because it seems obvious that there are more integers than positive integers. But when you map it like this, where's the evidence? For any number that you could ask on the bottom, there exists a number on the top. For every number on the top, there exists a number on the bottom. So how could we prove that this set is larger than this set? you need to have some unmappable element of this set that doesn't have an associated element of this set in order to be able to show that. Since we can't do that, we state that they are the same size. What do we think about that? Is that strange or weird to think that all integers is the same size as the positive integers? Infinity starts to mess with your brain a little bit the more you think about it, but yeah,
I think even by the definition of what it's the diagonal proof for 0 to 1,
yeah, Cantor's diagonalization, we'll actually go over that.
because that kind of proves it in and of itself, because it's unbounded in one direction, it's equivalent to unbounded in both directions because it's unbounded.
Yeah.
Whereas is the diagonal, it's greater magnitude infinity
Yeah,
because of the fact of how you get to that infinite. That's it.
yeah. So the key insight is that there is a function of converting one set into the other. And that function means, as the way that you're used to thinking of it, for every x, there is a y. For every top, there is a bottom. For every bottom, there is a top. There is a function that states that we can map between these two. So that's really interesting. Now the one that's really going to blow people's mind. How about the set of rational numbers? So rational numbers are all numbers that can be represented as a fraction, numerator over denominator. There are some rational numbers that are smaller than 1. There are some rational numbers that are really, really large. Could we come up with a starting point and a method for iterating every possible rational number to the point where I give you a rational number and you tell me the position in this algorithm? Eventually, it will generate it on this step. 1 then 2?
I think if I remember from the Cantor's diagonal proof, no, because
This is different from Cantor's. Cantor's asks about real numbers between 0 and 1.
This is just a guess, but every time you increase n, could you create like the power set of every previous element where it's like the numerator and the denominator of your combination? So that every time you increase it.
Really close. That's really close. This is possible. And the trick to this is to imagine it in 2 dimensions. So what we're going to have, since we are usually row, let's put the numerator here, let's put the denominator here. And we know that numerators and denominators have to be whole numbers. So we're just going to start listing the natural numbers, both of which we know is countable. But these go on forever. So if you ever tried to do something like iterate the first row would never finish, right? You would say 1, 1/2, 1/3, 1/4, 1/5, 1/6, etc. That would never finish. We would never get to 2. How could we change how our algorithm goes over this in order to get full coverage? What do we do?
1, 1, 2, 1, 1, 2, 2.
Yeah, it ends up being a diagonal. Basically, we're going to do that. And then for any number you could give me, we could tell you how long it would take to get there. Is there a rational number, any rational number, that this process would not reach, given infinite time? And the answer is no. This will hit every rational number. It'll take a long time. 1 over 1, 2 over 2, 3 over 3, 4 over 4 all represent the same quantity, but that doesn't matter. Because it doesn't prevent us from getting to the next rational number that we haven't considered yet. So because of this, we can state that all of these sets are in fact countable, which is kind of wild. That means they're also all the same size, because we can map a function from one onto the other. How about sets that are uncountable? Any examples of sets that we just can't enumerate? Let's go back one first then two.
Irrational numbers?
So we talked about rational and real numbers.
Irrational.
Irrational. Irrational. Okay, so things like pi.
That was my first thought.
Yeah, so real numbers include all rational numbers, but also include any number that might go on forever, never repeat, or do repeat, but that would be rational. So yeah, how do you, even just generating all numbers, all real numbers between 0 and 1? It seems for a moment like we could do this. You could just start with, all right, I'm going to, this doesn't really exist, 0.0, that's just 0. But it is a real number between 0 and 1. So let's do 0.0, 0.1, 0.2, etc. up to 0.9. Then 0.00, 0.01, 0.02, etc. all the way to 0.99. And then just continue this process forever. Each one of these would be growing in size. You'd have 10 times more in each column than you did in the prior column. Any issues?
Well, isn't it like Zeno's paradox, where like you just keep going halfway to the next destination, but you'll never reach 1, so then how do you get past 1?
Well, we're just looking for real numbers between 0 and 1 for the moment, let alone real numbers larger than 1 or smaller. We're isolating it to between 0 and 1 for the moment. But even then, there is a rational number that we'll never get to. What is a rational number that we would never state? We could just add 1 here. Why not? What's another number here that we won't get to?
0.991.
Any real fraction that goes on forever, like 1/3. We can get arbitrarily close as we go out here, but we're never going to hit exactly 1/3. There's always some margin of error on that. So we never generate that rational number. Same thing with 1/9. Anything else that repeats forever, we will not generate. This would give us anything that does terminate, but nothing else than that. So we'll actually talk about Cantor's diagonalization and why that, how we actually prove that we can't enumerate every real number between 0 and 1. But it's really intriguing. So, set of real numbers countable? No. So basically, for any countable set, we can prove that it's countable if we can come up with an enumeration procedure, which basically works like, where's a starting point and how do you generate the next one? So what is that enumeration procedure that lets you continue to spit out new values? The proof being there is no number that this algorithm won't eventually get to. Doesn't matter how long it takes to get there. It's just a matter of will it ever get there? So it is an algorithm. Even though this process doesn't terminate, we can reason about it. We can use something like induction, an inductive proof, to be able to show that there is no number that doesn't get reached. It's not like this process terminates, but we can mathematically show that there does not exist a number that we wouldn't get to, an element of the set that we wouldn't get to. So because we can reason about it, we can make mathematical claims about it because it's well-defined and it's predictable. By using the same algorithm, by using that same inductive idea, that process doesn't ever change. And because the process never changes, we can analyze its behavior in extremes. Because we can do this, we can also simulate it in a Turing machine. Because it is well-defined and has predictable results, it can be something that we can task a Turing machine to do. Even though it would never terminate, we can still talk about what the behavior would be like if we set a Turing machine to count the positive integers from now until we all perish, until the Earth perishes. We could talk about that defined behavior. So as an example, let's say we have an input alphabet A, B, and C, and the set is the positive closure of that input language. So we're going to say we have one or more of these characters is this set countable, first and foremost? All of the strings that could be generated by the positive closure of an alphabet A, B, and C. Who thinks, yes, it's countable? Some people. Who thinks, no, it's not countable? Who has no idea? The other half of the class, excellent. So let's take a look at what it might look like. How do I want to do this? Let's start with listing all strings in alphabetical order. Is this an enumeration procedure? Meaning that for every string in this language, we eventually get to it with this procedure. So we would start with A, and then AA, and then AAA, and then AAAA. It's not an enumeration procedure because it never produces B. We have an infinite number of A's that we need to get to in each string, everything between length 1 and length infinity, even though it doesn't exist. That process won't terminate. Does that mean that this set is not countable?
So no, it's not an enumeration procedure.
Well, we don't know that yet. Yeah, is there a way to count this set that's not listing strings in alphabetical order?
Would a regular expression count as an enumeration technique?
No, because it would define the language or define a subset of this language. We're basically saying this is the most generic language you can make with these characters. Literally everything except for the empty string is accepted, as long as you're only using these characters. So a regular expression for that would just have to define that language. But when we invent algorithms, what we're doing is we're coming up with the process that achieves the desired result. There are many different algorithms that we can apply toward a problem. Some of those algorithms won't solve the problem or partially solve the problem. But there are different algorithms for that same result. So this is not an enumeration procedure that works. But there is one that does. Can anyone see it?
You just do that, starting on A and then B and then C and then kind of interleave them.
Length order.
Like if you did it length order.
Yeah, length order works. So we would start, since it's the positive closure, start out with, I'll just start over here, everything of length 1, A, and then B, and then C. Now we're going to consider everything of length 2. So we would have AA, AB, AC, BA, BB, BC, CA, CB, CC, and this process would continue. Now you would have all of the length 3 strings, all of the length 4 strings, all of the length 5 strings. Now you can reduce this down into counting the positive integers, except that for each positive integer, there's going to be some combinatoric in terms of the number of strings that we need to handle at that length, but that will also be finite, so we know that it terminates. Regardless of the length, if we said how many strings of length 1000 are there, that's a finite number. It's a large finite number, but it's finite. Given an infinitely powerful computer, or something that's arbitrarily close to infinitely powerful, we could process that in a reasonable amount of time.
Would we just be able to calculate all the combinations by sum n to the number of characters within the alphabet?
It actually is even easier than that because this is kind of permutation. We don't care about the order. So because of that, how many choices do we have for the first character? 3. How many choices do we have for the second character? 3. It doesn't actually change. So you get 3 times 3, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Right.
So we have 3 to the first, 3 squared. It's 3 to the power of the length.
That's exactly what I was talking about.
Yeah.
Some number to the power of the numbers of letters, number of the letters within the alphabet. So
Yeah.
n to the length of the alphabet.
Yep. Yep. So every time it's going to be finite. It's going to be really long. It's going to be really complicated. It's going to take forever, but it is possible. So let's get rid of this. So the important conclusion from this is that different procedures can either be enumeration procedures or not be enumeration procedures, and you have to be especially cognizant of that when it involves infinity, because sometimes you won't reach the end of a row, so you can't do something like a row-wise iteration or a column-wise iteration. You have to start thinking about diagonals or some way, if there's a there's multidimensionality to your data, how do you parse that in some way that does explore the entire infinite state space in some well-defined order? What does this mean? Turing machines are countable. So as I mentioned earlier, you can now generate an arbitrary number of instructions. Some of those will map to Turing machines, but there exists an algorithm that will iterate every possible Turing machine. Again, extremely long, convoluted process that doesn't necessarily, it won't finish and it won't do anything meaningful in a meaningful amount of time, but this is a massive theoretical result that we could write an algorithm to produce every possible program that could be written. Yes, if you can actually do that in a way that makes, that is reasonable, that would unlock a crazy amount of power. So we're gonna make one more aside and talk about this concept called a linear bounded automata. So there aren't many changes we can make to a Turing machine to make it more powerful, and in fact, nothing we have found so far has made a Turing machine more powerful. But it might be worth thinking, all right, are there reasonable ways to limit the power of a Turing machine? Can we reduce the power or reduce the complexity of it? And in what meaningful ways can we understand different classes of languages? And the reason we might want to study this is if you can limit the Turing machine, then maybe it leads to more efficiency with regards to accepting or rejecting. So for instance, the NPDA that we studied is just a non-deterministic Turing machine with the tape restricted such that it has to be interacted with like a stack. That really is all that an NPDA is. So we could simulate an NPDA on a Turing machine just by saying the tape is a stack. The last thing we read and wrote to is the first thing we have to read from. You can't go back in history. Another interesting limitation to a Turing machine is just allowing access to just a finite portion of the tape. This is exactly like a finite state machine. It has a limited amount of memory, a finite amount of memory. Therefore, we can solve all of the problems that we can, keeping track of a historyless but finite amount of memory machine. What are all of the problems you could solve with a 5-state DFA? Doesn't matter how you design all the transitions within that, but you're only allowed 5 states. What's the complexity of the kind of problem that you can solve with that versus not solve with that? That kind of question maps directly onto a Turing machine with a limited amount of space on the tape. The really interesting question comes when we ask, okay, we know we need enough space to allow for the input, but what if we don't allow for more memory than the input allows us? So we can't now read the input and start working on some memory on the side. We have to be manipulating the input as part of the memory that we are using. So the longer the input, the more memory we have. The shorter the input, the less memory we have. Does that create a restriction on a Turing machine that leads to less computational power? So there's still no bound on the size of the input. It can still be arbitrarily long, but we just cannot access out of bounds of that input. To do this, we would have special symbols that represent the left bookend and the right bookend that says you cannot read past this, access past this, write past this in any capacity. We also can't rewrite these end markers. They are roadblocks. We cannot move the read write head left from the left end marker or right from the right end marker. They're just stuck there. We can also make it non-deterministic because we've shown that non-determinism doesn't really add any extra power. So we could make it non-deterministic. We can also state that it can have multiple tracks. Those tracks have to be bounded to the same size as the first track, since we've shown that those are equivalent. Does this restrict what we can do? The answer is surprisingly yes. Let's take an example of a language that may or may not be possible to do with a linear bounded automata. Find a linear bounded automata that accepts a to the n factorial. We need to know whether the number of a's on the input tape is a factorial without using any extra space. Any thoughts on how we might be able to do that?
Have to do a log of a to the n in some way to try to establish that it's equivalent to some factorial.
A log would be the inverse of an exponential. So if the question were something with regards to an exponential, that might make some sense. Good idea.
I think the question is, what is the inverse of a factorial?
I don't think we need to, okay, I can see where you're coming from, and I can see how that could possibly lead you to an answer. How do we calculate that factorial? How do we know intuitively that it's a factorial? Without thinking about it algorithmically, really. I give you the number 120 because we've seen that a couple of times. How do we know that 120 is a factorial? We'd have to know what factorial it is to know which number to start with at the high end. But do we need to know that starting at the low end? Divide 120 by 2. Is it a whole number? Yes, it is 60. Take that remainder, that number that's left, divide it by 3. Is that number whole? It's 20. Great. Divide that by 4. That's 5. Great. Divide it by 5. Since we end with exactly 1 after that successive division, we know that it is a factorial. So the process we're going to use is we're just going to look at all of the A's on the tape. We're going to now turn every other one of them into some, I've parsed this or read this character. So there are 120 A's on the tape. We'd have AX, 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 AX. At some point, we reach the end of the string and see the last thing we did was turn something into an X. Great. There are no A's after that. So now there are still 120 characters on the tape, but we go back to the left bookmark and say, now we're going to look for A's and divide this by 3. So A, the next A we see gets turned into an X. The next A we see gets turned into an X. The next A we leave alone. The next day we turn into an X, the next day we turn into an X. And continue this process, and you'll see that the last thing you do is turn something into an X. Divisible by 3. Go back to the beginning.
You keep track of what number you divide by.
That would be embedded in a state. We would be able to say something like, we can now, and it's also something we can use a second tape for of that exact same size, because we know that a factorial, like what we're dividing by, is never going to be larger than the number that we are looking at. But you could also use the, like when you change the first A, you could keep track of the fact that how many X's are in a row. You could read how many X's are in a row and then use that as a counter and a storage. If you could use one of the X places to hold that.
You talk about this theoretical second tape. Its length of the second tape is the same as the input, not that it's like both tapes lengths are equal to the input.
Both tape lengths are equal to, yeah. So we accept there's a single A left on the tape at the end of this, we reject otherwise. We would either need a second tape or something to keep track of the divisor. What will the transitions look like? We can think about that. But the really interesting question, now that we can kind of see how there are some problems where you would need that extra space linearly as well. Is it more or less powerful than an NPDA? Thoughts on that? Is this something that we could do with an NPDA? Not easily. So it is more powerful than the class of context-free languages. How about unbounded Turing machines? We already said they are less powerful than that. And I won't go into the exact proof, but the proof is in the textbook if you'd like to go see that proof. But they are in fact less powerful. So this is an interesting class of languages that exists between context-free and Turing machine. It turns out to be one of the few relevant classes of languages between those two bounds. Questions on any of this reasoning or any of these results? We're getting into the real fun now, as we start to talk about hierarchy of languages and automata, now that we've actually seen enough of the different classes that we can start talking about how they relate to each other. And also some classes of languages that are outside of the scope of what a Turing machine can calculate. So I'm motivated, that's probably all we have time for, but we only really care about classes of languages that have some kind of use outside of just they're interesting and they're different, because there are going to be an infinite number of different classes of languages that have different computational power, but which ones of those map onto something that we're actually interested in as computer scientists? So some of them involve languages that a Turing machine can operate on. Others involve things like taking out all restrictions to grammars. And you might think that context-free languages removed all of those restrictions. You would be wrong. There is something that we can do yet that creates absolute insanity in grammars that we will eventually talk about. So the first one we are going to briefly introduce, and I don't really have time to go into any detail on this, is the concept of recursively enumerable language. So we can define it real quick before we go as there needs to be some Turing machine that accepts it. The big star point here that says there's a big consideration here is that nothing is mentioned about what happens if we do not accept the string. We've seen a couple of these classes of languages where we can answer yes, but trying to answer no spins forever. An example of that was the losing it now, but the two grammars that represent the same language. We could say yes, we could say no, we've found a distinction. Here is a string that this grammar accepts that this grammar doesn't. That terminates with finality. But on the other hand, we just keep seeing string after string that both grammars can produce. Do they represent the same language? We don't know. So anything that can either accept or reject and not do the opposite is recursively enumerable. So we do allow the Turing machine to go into an infinite loop and never halt. It's just that if the answer is yes, then it will tell us yes in a finite amount of time. Or if the answer is no, it will tell us in a finite amount of time. But the other one we can't make any claims about. This is a language class that is more powerful than the algorithmic language class that a Turing machine can recognize. Because we needed a Turing machine to be able to halt after a finite number of steps. Whereas for the recursively enumerable language, we relaxed one of those two restrictions and say, we can make an interesting claim about half of one of the two decisions, and we will never be able to conclude the other. So we will come back tomorrow and talk more in detail about recursively enumerable and recursive languages. I have office hours starting out for any of the homework questions or exam studying questions or other questions. We'll see you tomorrow.